This may be the biggest transformation ever attempted inside a Tesla factory. It starts deep inside Giga, Texas. Elon Musk is preparing to tear out a massive portion of what traditional car manufacturing looks like. Entire forests of robotic arms, miles of conveyors, and countless individual parts are on the chopping block. In their place, Tesla is betting on something so extreme that it has the entire global auto industry watching closely. The company has revealed plans for a gigapress upgrade so large and so powerful that it pushes the boundaries of mechanical engineering itself. This is not just a slightly bigger casting machine. It is a fundamental rethinking of how a car is. Built from the ground up, and it could permanently change the economics of making vehicles. To understand why this matters, you have to understand how cars are traditionally built. For over a century, vehicle manufacturing has relied on assembling hundreds, sometimes thousands, of stamped steel components. Each of those parts must be formed, transported, positioned, welded, inspected, and aligned with extreme precision. Entire factory floors are dedicated to this process, filled with robotic welding arms working non-stop. Every additional part adds cost, time, weight, and complexity. Tesla's vision flips this logic on its head. Instead of assembling hundreds of pieces, the idea is to cast huge sections of the vehicle, or even the entire chassis, as a single solid piece of aluminum, produced in one shot. This is where the super gigapress comes in. Imagine molten aluminum, injected into a mold the way plastic is injected to make a toy. Now scale that concept up to the size of an entire vehicle structure. That is essentially what Tesla is aiming to do. While competitors are proud of machines in the 16,000 tune range, Tesla is pushing toward an almost unbelievable 50,000 tons of clamping force. The number itself sounds abstract, but its implications are very real. That level of force allows for enormous molds, huge volumes of molten metal, and castings that are far thicker and more structurally complex than anything that has come before. The global race to build larger casting machines has been accelerating rapidly. Tesla shocked the industry when it introduced a 6,000 tune press for the Model Y. That alone was enough to collapse dozens of parts into single front and rear underbody castings. China responded quickly, rolling out 7,000 tune systems of its own. Tesla then escalated again, deploying a 9,000 tune press for the Cybertruck, pushing the limits of aluminum casting even further. Chinese automaker Xpeng answered with a 16,000-ton hypercasting machine, currently the largest publicly known system in operation. For a moment, it seemed like China had seized the lead. But Elon Musk does not compete incrementally. Instead of matching 16,000 tons, or even slightly surpassing it, Tesla appears ready to leap straight to 50,000 tons. That is not a small step forward. It is a massive jump that changes what is physically possible inside a factory. To be clear, the 50,000-ton figure does not refer to the weight of the machine. It refers to the clamping force, the force used to hold the mold shut while molten aluminum is injected at high pressure. In engineering terms, that translates to roughly 500,000 kilonewtons of force, more than 3 times what even the largest Chinese systems can currently deliver. This level of force opens up entirely new possibilities. With smaller presses, manufacturers can cast individual sections of a vehicle, such as a front or rear underbody. With enough force, however, Tesla can use much larger molds that combine multiple sections into one casting. In the most extreme case, this could mean casting the entire unibody structure of a vehicle in a single shot. That is a radical departure from traditional manufacturing, and even from Tesla's own current approach. One of the most important advantages of this system is speed. Casting is fast. Once the mold is closed and the metal is injected, the process takes seconds, not minutes. If Tesla's claims hold true, a vehicle structure could be produced in under 5 seconds. That does not mean a fully assembled car rolls out every 5 seconds, but it does mean the most complex and time-consuming part of the build process becomes incredibly fast. When you eliminate thousands of welding steps and hundreds of robots, production lines become shorter, simpler, and far more efficient. Another major benefit is factory footprint. Traditional body shops take up enormous amounts of space. By replacing long lines of stamping presses and welding robots with a small number of massive casting machines, Tesla can dramatically shrink the amount of factory floor space needed per vehicle. That means lower construction costs for new factories, faster ramp-ups, and the ability to scale production much more quickly than legacy automakers. Weight reduction is another key factor. Every weld, bracket, and overlapping joint adds mass. A single large casting can be optimized for strength and rigidity while using less material overall. Thicker sections can be placed only where needed, and unnecessary reinforcements can be eliminated. The result is a lighter vehicle with improved structural integrity, which directly benefits efficiency, range, and performance. Cost savings may be the most important outcome of all. Each robot removed from the line saves not only the cost of the robot itself, but also maintenance, programming, energy consumption, and floor space. Fewer parts mean fewer suppliers, less logistics complexity, and lower inventory costs. Of these savings compound over millions of vehicles, the reduction in cost per car can be enormous. This is why many believe this technology is a critical piece of Tesla's plan to deliver truly affordable electric vehicles to the mass market. Chinese manufacturers like XPeng have already demonstrated the power of large-scale casting. Their 16,000-ton machine can produce massive underbody components, collapsing thousands of individual parts into just 2 large castings. This has allowed them to reduce production time and costs significantly. But Tesla's proposed 50,000-ton system goes far beyond this. Instead of casting one section per cycle, Tesla's machine is designed to cast multiple vehicle chassis at the same time. In some projections, that number is as high as 5 full chassis per cycle. This multi-cavity approach is crucial. It means that even if each casting cycle takes slightly longer due to the sheer volume of material involved, the output per cycle is dramatically higher. This is how Tesla can talk about production speeds measured in seconds per vehicle. It is not just about a bigger press, but about a fundamentally different production strategy built around scale and parallel output. The engineering challenges involved are immense. Handling such large volumes of molten aluminum requires extremely precise temperature control. The molds must be engineered to withstand enormous pressures without deforming. Cooling must be carefully managed to prevent defects, warping, or internal stresses. Even the foundations of the factory must be reinforced to handle the forces involved. These machines weigh millions of pounds and operate with tolerances measured in fractions of a millimeter. Achieving absolute precision at this scale is a monumental task, yet this is exactly the kind of challenge Tesla thrives on. The company has repeatedly shown a willingness to tackle problems others consider impractical by tightly integrating design, engineering, and manufacturing. Tesla can optimize vehicles specifically for casting rather than adapting casting to existing designs. This design for manufacturing approach is one of Tesla's greatest advantages. If successful, the 50,000-ton Super Giga Press could mark the beginning of the end for traditional automotive manufacturing methods. Legacy automakers are heavily invested in stamping plants, welding lines, and supply chains built around thousands of individual components. Transitioning to gigacasting at this scale would require... Is this the secret weapon that allows Tesla to finally deliver electric cars affordable enough for every household? Or is it a risky bet that pushes the limits too far? If history is any guide, Tesla is willing to take that risk. And if the Super Giga Press performs as promised, the shockwaves will be felt across the entire automotive world for decades to come. Recently, Elon Musk has made a series of important announcements surrounding Tesla's long-anticipated robotaxi program. According to Musk, Tesla's autonomous ride-hailing system is already operating without human supervision on selected routes, navigating real streets and traffic conditions on its own. While that sounds like a major milestone, many observers, including us, were hesitant to focus too heavily on the cybercab at this stage. The reason is simple. Despite the headlines, the vehicle is still in a testing phase and is nowhere near operating at large scale. Mass production has been discussed for months, with earlier expectations pointing toward an April start. But recent comments from Musk suggest that the reality will be far more complicated. A more serious issue has now come into view. Elon Musk has confirmed that mass production of the Tesla Cybercab will move extremely slowly in its early stages. This single statement has wide-ranging implications. It signals that the rollout timeline may be pushed back even further than many people originally expected. For a company known for ambitious timelines and bold promises, the phrase agonizingly slow immediately caught attention across the EV and tech communities. Many analysts and Tesla followers believe this slow ramp is directly connected to the radical design changes we've seen with the Cybercab. This is precisely why the Cybercab deserves a deeper look right now. The real story is not just about delays or timelines, but about why Tesla is choosing this path in the first place. Is this slow start ultimately going to benefit users? Or will it put Tesla at a disadvantage as competitors race ahead with more conventional autonomous vehicles? When Musk says that early production of the Cybercab will be agonizingly slow, longtime Tesla observers hear echoes of the past. It brings back memories of the Model 3 production hell, when Tesla struggled to scale manufacturing fast enough to meet demand. Others recall the early days of the Cybertruck, marked by delays, design revisions, and manufacturing challenges that stretched far beyond initial expectations. To some, this language sounds like another warning sign, another ambitious project facing the harsh realities of production. However, there is a second part to Musk's statement that often gets overlooked. He has emphasized that this slow pace applies only to the very beginning. Once production stabilizes and the process finds its rhythm, Tesla expects the ramp-up to accelerate dramatically. According to Musk, this is not a sign of failure, but a predictable phase in the life cycle of a completely new product. Some Tesla watchers, including well-known commentator Sawyer Merritt, have expressed confidence in this timeline, arguing that Tesla has repeatedly demonstrated its ability to move from chaos to efficiency once the fundamentals are in place. Musk has long explained that manufacturing growth follows an S-curve. In the early phase, output is slow and progress appears painful. This is not because something is broken, but because everything is new. Processes have to be invented. Machinery must be fine-tuned, and workers need time to adapt. As systems mature, output begins to climb rapidly, often faster than outsiders expect. Eventually, growth levels off again as production reaches its natural limits. The key challenge with the Cybercab is that almost nothing about it is familiar. The fewer parts, processes, and designs a factory can reuse, the slower the initial ramp must be. In Tesla's case, the Cybercab shares very little with existing vehicles. This is not a modified Model Y or a simplified version of an existing sedan repurposed for ride-hailing. It is a clean-sheet design built from the ground up for one purpose only: fully autonomous transportation. There is no steering wheel. There are no pedals. There's no traditional driver interface. This alone places the Cybercab in a category that no mass-produced vehicle has ever occupied. From a regulatory perspective, from a manufacturing standpoint, and from an operational standpoint, Tesla is moving into territory where there is no established playbook. Every assumption that normally guides vehicle production has to be re-examined. For generations, the auto industry, especially in Detroit, perfected the art of incremental improvement. New models were built on old platforms, familiar engines, were refined year after year. Changes were evolutionary, not revolutionary. Tesla's approach with the Cybercab is the opposite. Instead of adapting an existing vehicle and slowly removing the driver, Tesla is designing a vehicle that never had a driver to begin with. To traditional automakers, this may seem unnecessarily risky. Why not take a proven platform and adapt it gradually? Why not keep a steering wheel and pedals as a backup? Why not ease regulators and consumers into the idea of autonomy rather than forcing a radical shift all at once? The answer, according to Tesla's long-term strategy, comes down to cost. Cost determines everything that follows. Tesla's robotaxi vision only works if the vehicle can be produced cheaply. In massive volumes and operated with minimal human involvement, a vehicle designed around a human driver carries inherent inefficiencies: steering systems, pedals, Dashboards and driver-focused ergonomics all add complexity, cost, and weight. Removing these elements from the design allows Tesla to rethink the entire structure of the vehicle. By eliminating the driver, Tesla can simplify manufacturing, reduce parts count, and optimize the interior purely for passengers. Over time, this could result in a vehicle that is significantly cheaper to build and maintain than any adapted human-driven car. But achieving this requires reinventing not just the car, but the factory that builds it. This is where the slow production ramp becomes a requirement rather than a problem. Tesla is not just building a new vehicle, it is building a new production system alongside it. New casting techniques, new assembly methods, and new software-driven maintenance scheduling and customer experience all have to be reimagined. Tesla is effectively building a transportation service, not just selling a car. That shift requires infrastructure, software, and operational expertise that takes time to develop. For users, the question is whether this slow start will ultimately pay off. In the short term, it almost certainly means fewer vehicles on the road and limited availability. Early access may be restricted to specific cities or routes, and expansion will likely be cautious. This could frustrate those eager to see robo-taxis deployed at scale as soon as possible. In the long term, however, the potential benefits are substantial. If Tesla succeeds, the Cybercab could deliver rides at a fraction of the cost of traditional ride-hailing services. Without drivers, operating expenses drop dramatically. With a purpose-built design, maintenance could be simpler and more predictable. Over time, this could make autonomous transportation more affordable and more accessible than ever before. There is also a strategic advantage in committing fully to autonomy rather than hedging with hybrid solutions. By designing the Cybercab specifically for driverless operation, Tesla avoids compromises that could limit performance or scalability later. While this increases risk in the short term, it could create a significant moat if Tesla's approach proves successful. Of course, success is not guaranteed. Technical challenges, regulatory pushback, and public perception all pose real risks. A single high-profile failure could slow adoption and invite stricter oversight. Competitors are also advancing, often taking more conservative approaches that may reach market sooner, even if they lack Tesla's long-term efficiency. Still, Tesla has a track record of betting big and pushing through painful early phases to reach scale. The Model 3 struggled mightily in its early days, but it eventually became one of the best-selling electric vehicles in the world. The Cybertruck faced skepticism and delays, yet it represents a bold rethinking of what a pickup truck can be. The Cybercab fits squarely into this pattern. The slow start is not a retreat, but a deliberate choice driven by the complexity and ambition of the project. Tesla is attempting something no automaker has done before at scale, and that reality makes speed in the early stages not just difficult, but undesirable. In the end, the real story behind the Cybercab is not about delay, but about intention. Tesla is prioritizing a foundation that can support massive scale over quick wins that might limit future growth. Whether this gamble pays off will depend on execution, regulation, and public trust. For now, the slow pace is a signal that Tesla understands just how high the stakes are and how much needs to be done to get this right.